Students, in today's lecture we're going to talk about implicit differentiation. And one example to motivate the topic would be the following. In this example we're going to find the equation of a tangent line. So given a circle x squared plus y squared equal to 100, find an equation of a tangent line at 8, 6. So we have the following situation. We have a circle and we have a 8, 6. And we would like to find an equation of a tangent line. So to find an equation of a tangent line, we need a couple of things. We need y function equal to f of x. We need the derivative. Why do we need the derivative? Because if we know the derivative, we know the slope. The slope would be derivative evaluated at x equal to 8. And then we can write the equation of a tangent line by using point-slope equation. So y minus y1 equals m times x minus x1, where x1, y1 is any point on the line. Any point on the line. So what is the problem in this exercise? The problem in this exercise, we don't really have the form y equal to f of x. Our form is x squared is equal to, not equal to, but x squared plus y squared equal to 100. So one thing we can do is solve for y. We can solve for y. So we subtract x squared from both sides. We're going to get y squared equal to 100 minus x squared. And then we're going to take a square root on both sides. But when we take a square root on both sides, we're going to get plus or minus square root of 100 minus x squared. 100 minus x squared. So let's try to think, what does it mean for our circle? For our circle, that means that the positive of 100 minus x squared will correspond to the top of the circle. So this would be positive square root of 100 minus x squared. And for the negative part of the square root, we're going to get the bottom part of the circle, which is negative 100 minus x squared. Since our point is in the top semicircle, we're going to use the positive 100 minus x squared. Alright, so let's try to go through the procedure. We would like to find the derivative of y. So our y is equal to f of x is equal to positive square root of 100 minus x squared. And we're going to find derivative of this function. We're going to apply the chain rule because the square root is the outside function and 100 minus x squared is the inside function. So it's going to be derivative of the square root, which is 1 over 2 square root of 100 minus x squared times the derivative of 100 minus x squared. And we have to find derivative of 100 minus x squared to finish this derivative. So we have 2 times the square root of 100 minus x squared in the denominator times derivative of 100 is 0, so we have a minus, and we have 2x. And we can clearly see that this 2 and this 2 we can divide. And our final answer for the derivative is negative x divided by square root of 100 minus x squared. We would like to evaluate this derivative at x equal 8. So we're going to plug it into the derivative to find the slope. So our slope m is equal to f prime evaluated at 8. So we have negative 8 divided by 100 minus 8 squared. So we have negative 8 divided by 100 minus 64, so it's a square root of 36, so it's negative 8 over 6, or negative 4 over 3. So finally we can write the equation of the tangent line. We have a point which is 8 comma 6. We have the slope m, which is negative 4 over 3. So the equation of the tangent line is y minus 6 equals to negative 4 over 3 x minus 8. And this is our answer. It's not written in the standard form, it's not written in the point-intercept form, so but it's fine. So we solve this problem, but what if our function would be the following? Let x cubed times sine of x times y plus y to the 5 plus y equal to 0. And we want to find y prime. We want to find y prime. Unfortunately, this one is really hard to solve for y. So it is very hard to solve for y. Very hard to solve for y. Right? So sometimes it's very hard to solve for y, or sometimes it's even impossible, but we still would like to find derivative of y. So we still want to find derivative of y. So let's redo the previous example without solving for y, just to see how it can be done a different way. So second way for the previous exercise. Alright, so again we have x squared plus y squared is equal to 100. But we're gonna think the following way. x squared is our variable, but our y is actually not just y, but it's a function of x which we can't or don't want to solve for. Alright, so it's not really y, but it's y of x as a function of x. So let's take derivative on both sides. Let's take derivative on both sides. So it's going to be derivative of x squared plus y of x squared equal to 100 derivative. So we use the sum rule, which means we have to find derivative of x squared. So derivative of x squared would be 2x. But for this function we have something squared, so we have to apply chain rule. Chain rule says find derivative of the outside function, which is something to the power 2, and multiply by the derivative of the inside function, which is y of x. So our rule first, 2 goes down, then we have y of x to the power 1 times the derivative of the inside function, which is derivative of y. And on the right side we get 0, since derivative of a constant is 0. Now we convert back y of x into the regular y. So we have 2x plus 2y times y prime is equal to 0. We can divide both sides by 2, and this would give us x plus y times y prime equal to 0. And now we can solve for y prime, since it was our ultimate goal. That was our ultimate goal. So we subtract x from both sides, we get y prime is equal to the negative x, and we divide both sides by y. So finally we have y prime equals negative x divided by y. And if we need to find the slope, we have a point slope at 8, 6, which we can plug in and get m equals negative. For x we put 8, for y we put 6, so we're gonna get negative 4 over 3. And finally we have the equation of the tangent line, which is y minus 6 equals negative 4 over 3 times x minus 8. And as you can clearly see, this is the same answer as we had before. So we used implicit differentiation. Implicit differentiation means we don't solve for y, but we treat y as a function of x. In the next lecture, we're going to practice with this implicit differentiation. See you next time.